Okay, so let's start today's lecture. We are going to discuss something which is which can be said to be of independent interest, and the basic problem is the following. So we have a prime number p, right? We have k, which is a p field, and we have L, which is a finite, let's take a finite Galois extension, right? And let G be the Galois group of L over K, right? Then this G acts on what? Of course, it acts on the additive group L plus. It acts on the multiplicative group L star. And it acts on various quotients of these things. For the one which we are interested in is L star modulo L star to the power P. Excuse me. So this group G acts on L star modulo L star to the power P, right? Okay. What we would like to determine is determine the structure of the FPG module L star modulo L star to the power P. That's a problem we are going to look at today. Now, let me go back and tell you why we are interested in this problem, right? So we are interested in this problem because let's go back to our field, P field K, right? And we had said that primitive extensions of K of degree P to the N. So we're given a field, P field K and an integer N. Then we have the set of primitive P extensions of degree P to the N of this field K. They were in bijection with what? The set of pairs. I think we had called them chi, comma, E, is it? No, it was not chi, it was rho, right? It's chi when you have, when n is equal to 1, but in general, just pairs rho, comma, E, where rho was an irreducible FP representation of something or the other, right? And E was some extension of the fixed field of the kernel of rho, etc. So you have to recall, I mean, it's not very important to recall what precisely rho and E were. The point is that once you have established this bijection between these primitive extensions of degree P to the N in which we are interested and such pairs, you have to now go back and classify such pairs. You have to write down such pairs. So what I did last time in the last week was to determine the possible irreducible FP representations of degree N of the absolute Galois group of K. That was what rho was. Now, this week, we are going to determine the possible E's. And it will turn out, essentially because of Kummer theory or Artin-Schreier theory, it will turn out that these E's that we want to determine, they come from, or they are given in terms of the Galois module structure that I talked about initially, that we are going to do this week. So it's not entirely true, because I have left out the characteristic P case. So what I need to, this Artin-Schreier case, so if in addition to what I've explained at the beginning, we have to look at the following thing as well. We have the same thing, this K is a P field, G is a finite Galois extension, right? It's a finite Galois extension. Then, and suppose that the characteristic of K is equal to P. Then G, of course, acts on L plus modulo PL plus. And this is an FP space, right? So it becomes an FPG module. FPG module. And the question is, what is its structure? What is its structure? So this is what we need when the characteristic is P. If the characteristic is 0, characteristic of K, of course, then we need the FPG module L star modulo L star to the power P, right? That's what I said in the beginning. I left this one out, so I'm recalling it. And this week, we are going to determine this FPG module structure of this and the FPG module structure of this. Well, not in complete generality, because we don't need it in this generality, and I don't know how to do it in this generality. We will do it when this G is basically, or rather, I mean, okay, it can be said in terms of G. It can, what can be said in terms of G? I mean, that the wild inertia group of G is trivial. That's one of the conditions. The second condition is that G is split. And the third condition, there's a technical condition which I need when the characteristic is 0, and that is that you have the L star, right? And you take the P torsion. This has order P. Namely, this is to say that this L contains a primitive pth root of unity if the characteristic of K is 0. So this is what we are going to do in this week. If you have not followed everything, it doesn't matter, because we are going to recall all this again. This was just an introduction and to let you know where we are headed. So now we are going to go into the details. Fine. So that's what it says. Let's read the abstract so that I'll tell you once again. Maybe there's something else we will do if time permits. So let's go through this. So P, as you know, is a prime number. K is a P field, which means a local field with finite residue field of characteristic P. And L is a finite Galois extension. G is the Galois group of L over K. Suppose that L is split over K. And what does that mean? Now this G is the Galois group of an extension of local fields. So it comes with a filtration. It has this inertia subgroup, right? This T is the inertia subgroup, right? So this inertia subgroup is, of course, normal inside G, and I have the quotient, this G mod G mod T, which is so it's L naught K. You have T here, you have G mod T here, and of course the whole group is G. And what is L naught? L naught is the maximal unramified extension of K in L. Okay. So the condition here that this L be a finite tamely ramified extension of K, and the condition that it be split amounts to asking that this exact sequence has a section. We want this exact sequence to have a section. That's the hypothesis under which we are going to do what we determine the structure of these Galois modules, and that's the case that we need. No? In any case, so suppose you have KL, it's a tame finite tame extension. Any finite tame extension, right? Doesn't even have to be Galois. Then you can always find some L prime containing L, which has all these properties, which is what? That first of all, it's a finite Galois tamely ramified extension, and it's also split. And in fact, further on, we will see that if in characteristic 0, we require the P torsion subgroup of L star to have order P. So L prime can be taken to have this property as well, that it has its P torsion group has order P. Huh? So what am I saying? I'm saying if K is a P field, L is a finite tamely ramified extension of K, then there exists L prime over K, which is what? It's finite, it's tame, it's Galois, it's split. It contains this and contains L, right? This is what is being said, and this is not very, it's not difficult to, in fact, it's obvious that you can always find for any L like this, for any L like this, there's an L prime like this having all these properties. That's kind of more or less obvious, right? So requiring it to be split and having all these properties is not really a restriction. Of course, requiring it to be tame is very much a restriction, and our method will not work if it's not tame. So let's get back to this. L is this, and here this exact sequence has a section. That's the hypothesis. But T, as I said, is the inertia group. Now, and what are we planning to do? We determine the structure of this FPG module, L star modulo L star to the power P, in characteristic 0, when the P torsion has order P, which is to say that L contains a primitive pth root of unity. That is the same as saying that the p torsion has order p. Okay. And in characteristic P, and we are going to determine the structure of this additive group in characteristic P. So in characteristic 0, we need the structure of this group under the hypothesis that there's a pth root of unity. But in characteristic P, we need the structure. Okay, this I don't need, but I can do it as well by the same method. So I'll do it in characteristic P as well. But what I need is the structure of this additive group, where, of course, this curly P is what is called the Artin-Schreier map, taking x to the power p minus x. It's an endomorphism of this additive group. It's written here, right? So that's one of the things that we want to do. And there's a main thing as far as our application to primitive extensions is concerned. That's all that is required. This thing, which we will do only if time permits, is not really required in our application to primitive extensions. But it's a beautiful thing. For example, what it says is that this last statement. What does it say? It says, suppose you have a P field K, you choose a separable algebraic closure of K, right? And you take gamma. I don't know whether this is the notation later. Maybe, yeah, this is not the same as this gamma. Let's call it curly G. So let's call it curly G. This is the Galois group, the so-called absolute Galois group of K, right? It's the Galois group of K tilde over K. Now, one of the applications of what we are going to do is that this group, of course, it's a profinite group, like the Galois group of the absolute Galois group of any field whatsoever, right? Is a profinite group. But what this, our determination, the fact that we are going to determine the Galois module structure says that in Cat, I need it to be of, okay, so now, if the characteristic of K is 0, then this G is finitely generated. As, of course, a profinite group. And this finitely generated can be even made more precise, that the number of, you can take just a K over QP, the degree, it's a finite degree because it's any P field of characteristic 0 is a finite extension of QP, plus 3 elements. It can be generated by just this many elements. That's going to be one of the applications if we have the time. But what happens if the characteristic is the characteristic of K is P, then of course G is not finitely generated. And here is a very nice exercise. So this is something which you should be able to do based upon what we have done in the previous lectures. And here's the exercise. What does it say? So it says that I have K is a P field of characteristic P. K tilde is the separable algebraic closure of K. G is this Galois group, the absolute Galois group of K. And you have to show that this G is not finitely generated as a profinite group. Of course, it cannot be finitely generated as an abstract group. Even ZP is not finitely generated as an abstract group, because an abstract group, if it's finitely generated, then it's countable. But this is not countable. But we know that it's finitely generated. It's generated by 1, right? 1 generates ZP as an additive group, right? As a profinite group. I mean, not as an additive abstract group. Fine. So, so I don't know whether I'll get the time to show that this absolute Galois group is finitely generated in the characteristic 0 case, and that this many elements suffice. But we will see. So let's start. The first part is actually going to be totally unrelated in some sense to P fields. I mean, so this section 1, or what is it? The introduction. So the introduction, I don't need to go into the introduction, right? Because that's what I've been telling you. So I don't need to go into the, so let's get to this section 2. And this section 2 is pure arithmetic, or it's pure combinatorics or something. It has nothing to do with P fields. I mean, you'll see that it's something about natural numbers, basically. Okay. So, and this is a lemma which I've taken from Iwasawa. Iwasawa, as you know, is one of the pioneers in number theory in the 20th century. So his ideas now are everywhere. So let's establish the notation. P as before is a prime number, and this E is some integer which is prime to P. Now, as you can see, the notation is so chosen that it sort of more or less corresponds to the situation where we are going to apply it. So we are going to apply it to P fields, and E is going to be some ramification index, and this condition that it be congruent to 0, I mean, that it be prime to P, just means that we are going to look at tame ramification. Okay, so next, now if P, if this E is prime to P, then the image of P in Z mod Ez is going to be invertible, right? This is the group of invertible elements. So that's the image of P, and this multiplicative group, in this multiplicative group, this P bar will have some order. So this G is not quite the order, but it's any multiple of the order of P bar in Z mod Ez star. Okay, that's the notation. I mean, you just take any multiple of the order. So what does that mean? If I take a multiple, then let's look at this Z mod Ez star. I have P bar here, And so then I'll have the subgroup generated by P bar, right? This is a subgroup generated by P bar. So it's a cyclic group of some order. And G is a multiple of that order. So if I look at this Z mod GZ, there's going to be a unique homomorphism of groups such that which takes 1 to this P bar, right? So I mean this is completely obvious, right? Or you could say that it takes J to the image of P bar to the J, I mean, or whatever. So this is my G. I mean, G is chosen such that it's a multiple of the order of P bar in Z mod EZ star. Yeah. So that there's a unique morphism of groups from Z mod EZ, not E, Z mod GZ to Z mod EZ star, which sends 1 to P. Okay. And let N, then you have this LCM of P minus 1 and E. But that's not N. N is a multiple of this LCM. And then you write your N. I mean, the LCM can be written as, it's a multiple of P minus 1 as well as of E, right? The LCM is the least common multiple. And N is a multiple of the NCM, so of the LCM. So this N is, of course, a multiple of P minus 1 and of E. And I'm defining C and D to be these coefficients. I mean, these N is C times P minus 1, and it's also D times E. Now, here's the important thing. Maybe we have already come across this notation, B upper I. What is this notation? So this B upper I is a sequence of positive integers, strictly positive integers, which are prime to P. And here's an explicit formula for these BIs, right? BI is equal to, you just take I and you add the integral part of I minus 1 upon P minus 1. So that's what BI is. So you will see that, I mean, if you take P equal to 2, then you'll see that, you know, this is simple, right? So let's see, I, BI, when I is 1, 2, 3, 4, etc. And this BI is going to be 1, 3, 5, 7, and so on. If P is equal to 2. If P is equal to 3, then you have I here, 1, 2, 3, 4, and BI here. So this is going to be 1, 2, then it's going to be 4 here, and 5, and so on. That's it. So that's what these BIs are. And finally, I mean, this is a big piece of notation which I've used very often. If you have two integers A and B, then this interval AB is the set of integers. It's a subset of Z consisting of those things which are between A and B, right? So for example, 1, 3, this is equal to 1, 2, 3, right? And 3, 1 is, of course, empty. Fine. So that was the notation. Now, the first statement is, I mean, it's something which you should be able to find a proof for yourself. I mean, it's not obvious at all, but it's not very deep, or it doesn't use any technology. I mean, it's just a counting argument, but you have to do it carefully. So look at this. It says, look at the map from 1 comma n. So that's this interval. It's an interval 1 comma n. And z mod gz, that's what it is. To z mod ez. What is this map? So if I is in the interval 1 to n, then it's taken to bi. That's the ith integer, positive integer, which is prime to p. And what is j taken to? J is taken to p to the power j. Remember, that is the map which I had explained here. I mean, 1 goes to p, but j goes to p to the j. Okay, good. And of course, you can multiply these two things. They are classes mod E. You can just multiply them, and that gives you a map from the interval 1 cross n times z mod gz to z mod ez. Okay? What is the claim? The claim is that this map is surjective and that every fiber has dg elements. There's a number of elements in each fiber, where d, of course, is this d here, which expressed n as d times e. That's the d. Okay? Right. So here's, I mean, this is a proof, and it's somewhat clever because, let me see. Now, here's what the idea of the proof is. Let me see. Yeah. So the idea is that this interval 1 comma n, it's going to be written as, so first of all, it is the union of these two successive intervals, 1 comma de. De is equal to n. So it's not 1 comma n, which is being written like this, is the interval 1 comma cp. Cp, c, remember, is again one of the coefficients here. It's n is equal to c times p minus 1. So you look at the interval 1 comma cp, it can be written as n plus, what is it? C, C, yeah. Plus C, yeah. So that's one way of decomposing this interval. And this is a disjoint union. Of course, I mean, these are two successive intervals. So this is, of course, disjoint. But it can also be written as that, and that is the thing which is less obvious, which is that it can also be written as the set of all bi, where I is in 1 to n, union, and the multiples of ip, where this p is in 1 to c. No, not p, of course. I is in 1 to c. And this is also disjoint. Okay? So I've written this set, this interval 1 comma cp, as the union of two these two successive intervals. I mean, this is actually n. So 1 comma n, this interval, union the interval n plus 1 comma n plus c. And so n plus c, you can check, has to be equal to c times p, right? So that's how these things are defined. But of course, this interval can also be written as the union of those, I mean, the subset consisting of those elements which are, those numbers which are prime to p and those which are multiples of p. Okay, so in some sense, what you have to calculate, what you have to compute is the contribution of these things which are prime to p, because that's how this map is defined, right? These prime to p things. Now, one way of, so the way to do it is compute the contribution of this and this and this. So what we are doing is, I mean, okay, let me write it this way. If you have written if you have some set and you have written it as S1 union S2, and you have also written it as T1 union T2, and if you know the number of elements in S1, S2, and T2, then of course you know the number of elements in T1. I mean, all these unions are disjoint unions, and right? Because if you, the number of elements, if you know S1 and S2, then you know how many elements there are in S. And if you know how many elements there are in T2, then you just subtract the number of elements in T2 from the number of elements in S. And that will give you the number of elements in T1, which is what we want. Here, what we are computing is not the number of elements in these things, not the number of elements. Sorry, I mean, I should not have erased this. It was, I think, 1 comma n, yeah, maybe union. So it's not the number of elements that we have to compute. We have to compute just the, I mean, we have to compute this contribution, which is defined here. The contribution of a subset S. So we will compute the contribution of this, the contribution of this, and the contribution of this. What we are really interested in is the contribution of this. But that is going to be the contribution of this plus this minus this, right? And what is this contribution? So contribution means this. So this is exactly what is required in order to prove this lemma, okay? So I'll leave it there. What this lemma does is to, I mean, the proof is, in the proof you have to contribute, you have to, wait a minute. Yeah. In fact, it's even better. Yeah. It's even better in the sense that you don't even have to compute the contributions of these two things and the contribution of this. What you prove is, so let me go back to this simple example. Suppose you have a set S, you've written it as S1 union S2, and also as T1 union T2. And what is it? Is the same as this. What you want to compute is the contribution of this. What is this? So if you show that these two have the same contribution, these two have the same number of elements, you don't have to compute any of them. You don't have to show how many elements each one has. You just have to show that they have the same number of elements. Then, of course, this T1 and S1 will have the same number of elements. So you just have to compute the number of elements in S1. So this is the thing that you do. It's simpler even than saying that you compute the number of elements this and this and subtract the number of elements here. You don't even have to do that. You just have to show that these two have the same number of elements. So the number of elements in T1 is going to be the same as the number of elements in S1. And that's the only thing that you have to compute. Okay. Right. Fine. So now that is purely, it has nothing to do with finite fields or P fields or anything. Huh? It just has to do with integers. Now I have to, I have a finite extension K of Fp. Q is the number of elements in this. L is a finite extension of this K, and F is the degree, and G is A times F. So G is what? A times F. So it means that the number of elements in L is P to the G, right? Because it's the number of elements in L is Q to the F, and Q is P to the A, right? So that's one. And AF is equal to G, so it's P to the G, right? Okay. And of course, this finite extension, it's a cyclic extension, right? L over K, and sigma is the Galois group. It has a canonical generator little sigma, which takes every element x in L to x to the power Q, right? Where Q is the number of elements in K. Now, one of the things that you need to recall is that as a K sigma module, L is free of rank 1. That's what follows from the so-called normal basis theorem. And I think we had given an elementary proof of this at some point in this situation. I mean, not for arbitrary fields, arbitrary Galois, finite Galois extensions, but for a finite field K, we had given a proof at some stage. So basically what it means, what this normal basis theorem says is that there's some element A, all whose Galois conjugates form a K basis of L. Okay. Then you have the groups T, G, and the character. I mean, these are things which are given to you. T is a subgroup of L star. It's more or less like what we had last time, right? So T, I'm taking T to be a subgroup of L star. E is the order of this group. So since E divides what? L star, the order of L star is Q to the F minus 1. So that's the same as saying that Q to the F is congruent to 1 mod E, right? This here. And theta is, I mean, that's just another notation for the inclusion. Then you have the group of characters, and this group of characters is actually cyclic, and it's generated, it's cyclic of order E because T is of order E, and it's actually generated by this character theta, right? That happens for any cyclic group. And since T itself is cyclic of order E, its automorphism group can be identified with Z mod EZ star, okay? And there's a unique morphism of groups from sigma to odd T, so that sigma goes to Q. Q is an element of Z mod EZ star because E is congruent to mod, 0 mod P. We must have taken it somewhere, right? Where is, yeah, E. I mean, it follows from whatever we have been doing, because this power of P is prime to E, right? So E is prime to P. So now we are making T into a sigma module. How do I make a group into a sigma module? I have to give a homomorphism of sigma to the group of automorphisms of that group, and that is what is given to me. I mean, take sigma to this Q, right? And therefore, when I do it, I can make this semi-direct product. And what I'm interested in, so I have this semi-direct product, and I also know the structure of this semi-direct product, right? It's generated by two elements, sigma and tau. Sigma to the power f is 1, tau to the power e is 1, and sigma, tau, sigma inverse, the conjugation action of sigma on tau raises tau to the power q. And this is exactly what happens for tame Galois groups, right, of p fields. This is when we discussed tame ramification. We must have seen this kind of things. Now I'm going to define a KG module LR, in which for R an integer, in which so sigma, of course, acts by raising. So what is this LR? The underlying K space is just L. And sigma continues to act as it does, because sigma is what? Sigma is the Galois group of L over K, and little sigma is the generator of capital sigma, which sends x to x to the power q, where q is the number of elements in little k, right? Okay. So sigma continues to act the way it does on L, but now I have to give you an action of this T. An element little t of capital T acts on an element x of L by, so I can look at theta t. Theta t, what is it an element of? It's an element of L star. And I can raise it to the power I, or R here. It's not called I, it's called R. Raise it to the power I, and then multiply with this x. So if R is equal to 1, then t dot x is just theta t times x. But if R is arbitrary, then I have to put this exponent R here. So that is, I get a kg. Before I can call it a G module, I have to check that. So, sigma or sigma t, sigma inverse is equal to t to the q for every t in capital T. So in order to define an action of G, I have to check that these two actions of sigma and T are compatible. I mean, compatible with this conjugation relation, with the conjugation action of sigma on T. And this is easy to check, because all you need to do is, I mean, you just look at sigma T, sigma inverse acting on X. What is it going to be? It's sigma T, then acting on sigma inverse of X, which is X to the power minus Q. But that is, then it is sigma acting on T, acting on this X to the power minus Q. So that's theta of T to the power R times X to the minus Q. Now sigma will raise everything to the power Q. So it's going to be theta T to the power RQ, and X So that's the same as theta of, what's that? What do I want to say? Okay, theta t to the cube, right? R times x. So that's t to the cube acting on x. So this is equal to this. I mean, in other words, the relation between sigma and t is satisfied. So that is what you need to check in order to say that, this is actually an action of G on L. Okay, so I get this G module, or KG module rather. I get a KG module LR. Okay. And it, of course, depends only on the image of R in Z mod EZ. Because, I mean, this here, because T has order E. Okay. Now, the important thing is, so for every I have this Li. I can take the sum over all I in Z mod Ez. As I said, this Li only depends upon the image of I in Z mod Ez. So I take the sum of all these things, and I get a Kg module. And the proposition says that this module is free of rank 1. So this is a simple proof, and you just take a look at it. And then here's so now I have this LR, it's an FPG module. I mean, okay, it is a KG module, so I can always think of it as an FPG module, right? And then this LG is an FPG algebra. So if you have a module over a ring A, then you can get and B is an A algebra, then of course you get a module over the ring B by just taking the tensor product. And that is what is happening here. This LR, so LR is being viewed as an FPG module, and this LG is being viewed as an FPG algebra. So I can get an LG module, and the point is that this is isomorphic to this. Now, what is this? So what does this mean, first of all? How can the sum of these powers of theta be a module? So theta, remember, is a homomorph, it's a character of t. So theta to the power I, and I can view, I mean, it's a character. So, this allows you to view L as a T module for various i's, for various i's, as a T module. So the direct sum, of course, is going to be a T module. But now what we are interested in is a G module structure. So you have to somehow say how sigma acts on this L space. You know how little t acts, because it acts through these characters, the various characters here. So now every element of this is a family like this, and this sigma is just permuting, and these families are indexed by Z mod GZ, where what was G? G, remember, was, so as I said, the number of elements in L was P to the power G. Okay. G is AF as in. So this is the next thing. So here's the proof. You just take a look at it. And then we have these FPG modules LR and LS, right? The point is that they are isomorphic if and only if theta to the power R and theta to the power S as characters of T are in the same phi orbit. So what is this phi now? This phi is the generator of the Galois group of L over Fp. This is generated by phi. So, this Galois group, this phi, let's just call it phi. Phi acts on L, of course. It acts on L star. It acts on T, which is a subgroup of L star, and therefore it acts on the characters of T. Okay. So what does it send the character chi to? It sends the character chi to the power P. Well, so I don't need the action on T really. It's just phi is acting on this only through this, no, not through this T business. Okay, so I think I'll stop here today because I'm not feeling well. So I have to go and take some rest. Okay, see you next week, next day after tomorrow.